Hi, this is Chris. In the last video, I covered the design and implementation of a floating point addition circuit for the IEEE 754 binary 16 format. In this video, I'm going to cover how to make the addition circuit use resources more efficiently. But before that, the last video ended with 3 study questions, so let's get started on those. Instead of computing the absolute value of some sig, why didn't I expand the test for augend and addend to see if when the exponents for the two operands are equal, which significand value is larger, and avoid having to take the absolute value when subtracting? As you can see from the code on the screen, this adds 2 additional tests to the if statement. The test I want to focus on is to see if A sig is less than B sig. I don't know how the Verilog compiler implements this test, but a common way to do this comparison is to subtract A sig minus B sig. Then we can examine the sign bit. If the sign bit is set, then A sig is indeed less than B sig. To do the subtraction, I could instantiate the module paddr42. But the reason for doing this extra test is to avoid having to use paddr42 to take the absolute value of some sig after subtracting the 2 significands. This doesn't save us any work. Also, the condition for the if statement would have to do the extra work of checking to see if A exp is equal to B exp. Since adding the extra test doesn't really save any time or gates, I opted to leave the if statement test simple and fix the sign of the significand on the back end. Here is the next study question. For the case when the 2 significands need to be subtracted, I added a for loop. I said that in the first pass through the loop that the loop tests for 8 leading zeros, then 4 leading zeros, 2 leading zeros, and finally 1 leading zero. Technically, this isn't true. How many leading zeros does each pass really test for, and why is the count different? You can see the code for normalizing the significand after subtraction on the screen now. The mask value is 42 bits wide. This is the same as the other significand registers augend sig, addend sig, and sum sig. When the mask value is declared, it's initialized to hold all ones. The first time through the for loop, the value of I is 8. Inside the for loop, the test condition for the if statement calculates the amount to shift the mask to test the bits. The first time through the loop, this expression evaluates to 32. So we shift in 32 zeros on the right side of the mask. This leaves ones in the 10 most significant bits of the mask register. These 2 extra bits are for the carryout and sign bits. Subsequent iterations of the for loop mask off the top 6, 4, and 3 bits respectively. Remember that we first compute some sig, then we take its absolute value. If there was a carryout, we renormalize by shifting 1 bit to the right. It's after this that we come to the for loop, so we know that the carryout bit and the sign bit will always be 0 because the for loop processes the data after we have computed the absolute value of the difference and after we've performed the optional right shift of the difference. On to the third and final study question from the last video. This implementation of the addition circuit calculates the exact value for the sum of the 2 input operands before rounding. Why is calculating the exact intermediate value of the sum of the significands a bad idea? Here's the declaration of the significand registers. Nsig contributes to the size of the significand registers, but its contribution is limited. Mainly the size of the significand registers is a function of Emax and Emin. The values of Emax and Emin are computed from powers of 2. This means that every additional bit in the exponent field effectively doubles the size of Emax and Emin, and consequently doubles the size of the significand registers. As the table shows, if we require that the intermediate sum of the significands be exact, the size of the significand registers is 277 bits for the binary 32 format, 2098 bits for the binary 64 format, and 32,878 bits for the binary 128-bit format. You can see that allocating space to exactly represent the significands quickly gets out of hand. We're going to have to select a much smaller form to hold the internal augend, addend, and sum significand values. This is going to involve compromise. We're not going to be able to compute the exact value for the sum's intermediate significand value. The good news is that only the final rounded stored significand is needed for the final result. If the intermediate significand value isn't exact, that's okay as long as the final rounded result is correct. The significand registers can be reduced to about 2 times nsig bits. You can see the new declaration of the significand registers here. Since the significands are smaller, we can replace the p-adder42 module with the smaller p-adder26 module. It should be clear that now when we compute the intermediate value for the significand of our sum, that we're no longer guaranteed to have an exact result. What isn't clear is when we round this new value for the significand to fit into our final 16-bit result, that we get the same value as when we computed the sum of the significands exactly. I'm not going to give a formal proof that the revised version of the adder is always correct. Instead, I'm going to walk you through an explanation of how I decided the number of bits of precision needed for the intermediate result, and then I'm going to explain how I tested that for all rounding modes that the less accurate intermediate result still yields the same final rounded result for all normal and subnormal operands. In the last video, I walked through the process of adding 1 point followed by 10 zeros times 2 to the 11th power and negative 1 point followed by 10 ones times 2 to the 10th power. I'm going to expand on that discussion. In this diagram, the augend sig, addend sig, and sum sig registers are pictured. The top register is the augend sig. If you look closely, you can see that the 11 bits holding the unshifted significand have a light green background. The other bits in the register have a white background and all contain 0. The middle register is the addend sig register, and it holds the right shifted significand. Like the augend sig register, the 11 bits holding the actual significand have a light green background. The remaining bits of the register have a white background, and again, all contain 0. The bottom register is the sum sig register. More precisely in this case, because the numbers being added have different signs, the sum sig register holds the difference of the augend sig and addend sig registers. As you should remember from the rounding videos, the value to be rounded is divided into 2 main parts, X bar and Y bar. The X bar bits are the bits which, after rounding, will become the significand of the binary 16 result. Like the bits in the 2 previous registers, the bits which will become the final significand have a light green background. All of the remaining bits to the right of the X bar bits are the Y bar bits. As was done in the rounding videos, Y bar is split into 2 parts: its most significant bit and the remainder of Y bar. You can see that the deciding bit has a light yellow background. The remainder of the Y bar bits have a light orange background. The least significant bit of X bar, the most significant bit of Y bar, and the remainder of Y bar, in conjunction with the rounding mode, determine how to round the whole of X bar. It's these 3 values which the rounding module uses to create the flag's last kept bit is odd, deciding bit is 1, and remaining bits are non-zero, respectively. If you don't remember the details of how the rounding module initializes these 3 flags, now would be a good time to review the source code for the rounding module. For this pair of operands, the difference of augend sig and addend sig is represented exactly. Before moving on, I want to remind you that if we're in this portion of the circuit, neither of the significands will be 0. We only use this portion of the circuit if both operands are normal or subnormal numbers. Whether an operand is a normal number or a subnormal number, the most significant bit of the significand will always be 1, so the significand will never be 0. This fact will become important later on. In the next slide, I've reduced the exponent of the addend by 1. This requires shifting the addend significand value one additional place to the right. Looking at the sum sig register, you can see that the location of the 11 most significant bits for the difference have moved left. These are the X bar bits. As always, just to the right of the X bar bits are the Y bar bits. And again, the deciding bit has a yellow background and the remainder of Y bar has an orange background. One other thing to note about the sum sig register, the least significant bit set to 1 is immediately below the least significant bit set to 1 of the addend significand. As I continue to reduce the exponent of the addend, the leading number of 1 bits in X bar expands. And the least significant bit in sum sig set to 1 moves right with the least significant bit of the right shifted addend. This pattern continues. At each step, one more bit at the top end of the significand becomes 1. And the least significant bit set to 1 moves right, following the least significant bit of the addend. You can see this pattern repeating as the exponent for the second operand is reduced, one step at a time, to -2. At this stage, I want to look at how many bits the addend has been shifted right. We compute the shift amount by subtracting the exponent of the addend from the exponent of the augend. In this case, the computation is 11 minus -2, which is 13. Note that up to this point, the significand registers are large enough so that we can compute an exact intermediate value for the significand. Because of this, there is no question that the values the code computes for last kept bit is odd, deciding bit is 1, and remaining bits are non-zero are correct. The question we're trying to answer is, if we limit how far the addend can be shifted to the right, will the rounding module still derive the correct values for these three quantities? Now that we're at the exponent -2, and we've shifted the addend to the limit of the allocated register space, something important changes. The string of 1 bits in the significand for the sum has spilled into the most significant bit of Y bar. That is, deciding bit is 1. Because from this point onward, the most significant bit of Y bar will always be 1 no matter how far we shift the addend to the right, the deciding bit will always be 1 forever after. Note something else. Because the addend has the largest possible significand value, and because the addend is being subtracted from the augend, we can see that using any smaller valid significand value for the addend will leave 1 bit set in the remaining bits of Y bar. Here, valid significand value means the most significant bit of the addend will always be 1. Only the bottom nsig bits, that is the bottom 10 bits of the significand for the binary 16 format, may ever be 0. We can see that from this point on, the deciding bit will always be 1 by making the augend, addend, and sum registers 1 bit larger, and by shifting the addend 1 bit farther to the right. With the additional bit, the registers would have these values. You should be able to see that from this point onward, the most significant bit of Y bar will always be 1, and the remainder of Y bar will never be 0. This should make clear why I claim it's not necessary to have the significand register be 42 bits wide, because even though Y bar may not be exact because we're using the shorter register size, the shorter register size will produce the correct values for last kept bit is odd, deciding bit is 1, and remaining bits are non-zero. Using the shorter register definitions does have some impact on the code. The first change is how the augend sig and addend sig registers are loaded. And because the significand registers can no longer represent the full dynamic range of the binary 16 floating point format, the code needs to limit the amount which the addend can be right shifted. This is the new code for shifting the addend. It's necessary to cap how far we shift addend sig to the right. If we didn't cap the shift amount, we would lose bits which are set to 1, and this would affect the computation of last kept bit is odd, deciding bit is 1, and remaining bits are non-zero. After shifting the addend significand, we come to the for loop to renormalize in the case that the addend gets subtracted from the augend. Here we need to change the computation for how far the mask register needs to be shifted. The next change is that because the significand registers are smaller, we can no longer use the p-adder42 module. It is replaced by the p-adder26 module. Next, the location of the overflow bit has moved. And the last change related to the size reduction of the significand registers is the instantiation of the round module. Observant viewers will note that I mentioned changing the location of the overflow bit, but not changing the location of the sign bit. This was implicit in changing the code to use the p-adder26 module. If you look closely at the argument list for the p-adder26 instantiation, which computes the absolute value, you'll see that the sign bit definition was also updated as part of that change. At this point, it would be good to revisit the table of how many bits are now required for each of the binary floating point formats. We achieved a significant reduction of resources. Not only are the registers much smaller than they would have been if we had insisted on having an exact intermediate result, but we also save resources by being able to use a smaller adder. The p-adder42 module has 560 lines of code. The p-adder26 module has 336 lines of code. I expect that the reduction in gates needed to implement the two adders will be proportionally similar. The next question is, does the floating point addition circuit really give us the correct rounded result? To answer this question, I built a test harness and compared the output of both adders for all possible positive and negative, normal and subnormal numbers. I ran the test across all 4 rounding modes. The GitHub repository for this video has the fp-addexact module and the new fp-add module and other pieces of code needed to compare the output of these two modules on a Digilent Basis 3 board. As a reminder, neither Digilent nor Xilinx sponsored this video. I have this particular hardware because it was required for one of the Verilog classes which I took. If you prefer other hardware, please feel free to port the code. If you do port the code, it would be great if you would pass the updates back to me so they could be incorporated into the GitHub repository. And yes, of course the code will be marked crediting you as the author of the changes. As mentioned earlier, the test harness generates all possible combinations for subnormal and normal numbers and passes them to both of the implementations of the floating point addition circuit for the binary 16 data format. If an error is found, execution of the test halts and the code displays the hexadecimal value DEAD on the 4-digit 7-segment display. If the test run is successful, the hexadecimal value AAAA is displayed. The rounding mode is selected using dip switches 0 through 3. Exactly one of these switches must be in the on position. All of the other switches must be in the off position. Time to look at the test harness in operation. I've put switch 0 in the on position to select the default rounding attribute round ties to even. As soon as the code is loaded, the test begins and will execute until all pairs of normal and subnormal operands have been tested. Again, if an error is found, execution stops immediately. As you can see, the test is completed now, and the 7-segment display reads A. I'll change the dip switches to select the round towards 0 mode and restart the test by pressing the right button to reset the code. Again, the test completed successfully. This test will now compare the results for the round toward positive attribute by setting switch 2 and clearing the other switches. Press the reset button to run. Another successful test. The final test is for the rounding mode, round toward negative. The final test is done. Now back to the slides. The final test was successful, but let me caution you about what the test means. This test harness does not prove that the addition circuit is correct for all possible normal and subnormal values. It only proves that the two versions of the circuit produce the same results for every pair of normal and subnormal inputs. Testing the circuit for correctness is a different problem. If the circuit which calculates the exact intermediate value of the sum produces an incorrect result, all this test has shown us is that the more efficient version of the addition circuit reproduces the error exactly. And you knew there was going to be a study question, right? I walked through an explanation of why, even though the new addition circuit doesn't exactly compute the intermediate result of the sum in all cases, that the rounding still happens correctly when the added significand is subtracted from the augend significand. Explain why, when the two significands are added rather than subtracted, rounding still works correctly. I plan to wrap up the adder in the next video. Wish me luck. There always seems to be one more topic which comes up as I prepare the scripts. The location of the GitHub repository with the code for this video can be found in the comment section for this video. Please share this video with friends and colleagues who might have an interest in this video series. Questions and comments are welcome in the comment section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.